Okay, I forgot to turn on the microphone. Okay, welcome back to the second part of today's lecture. This one is about computing photoelectron spectra, and we will, in a minute, begin with calculating the drift velocity and the drift energy. Are there questions so far on the, on this introduction to the model?
Regarding the first part of the example, here, what is the energy that it needs to have?
Yeah, this is the total energy of the electron. Yeah, so this that's a good point. Yeah, so this is, and the electron also possesses kinetic energy when bound in the to the nucleus. Yeah, the bound electron also has kinetic energy. Yeah, so this is the ionization potential. So we actually set this equal to the ionization potential, so not equal to the potential here. Yes?
Okay, there is the first energy that is EV equals half. What's that energy?
That's the ionization potential. That's the binding energy of the electron here, yes? So here this EIP. Okay. Shall we continue? Yeah, please.
And that total energy is the energy required to make the electron, the energy at the middle of the tunnel, at the middle of the potential, or
Yeah, so the actually the first Bohr, this would correspond to the energy of the electron in the 1s orbital in the hydrogen atom. So it would be mostly localized in the center, actually. Yeah, it's the wave function has the shape e to the minus r. E to the minus r over a naught. Yeah, so it's
consider the laser field in that area or in that region? Because for R, is this than the tunnel entrance? We should neglect the laser potential, right?
yeah. So when for the outside, on the outside you shouldn't neglect it, and on the inside we neglect it.
Okay, but here we didn't neglect it.
So the point of this was to calculate whether it's reasonable to neglect it. Yeah. So we ask the question: at what when is the influence of the laser electric field so strong that the energy of the electron would be significantly altered? Yeah. I think I make a remark to improve the script in the point. Okay. Now we have chapter 2.3, drift velocity and energy. Oops, 2.3. Drift velocity and energy. Okay, so we have seen so far that the electron performs an oscillatory motion, but there can also be a motion away from the nucleus. And this motion away from the nucleus, this drift, this is what we will focus now on. And for this, let us first consider that essentially all experiments that are conducted are in essentially all experiments, the measurement is conducted in the far field. This means the electron is detected at a distance that is much, much larger than the size of the laser focus or the wavelength. There's a notable exception in the literature, yeah, which I want to mention. Just need to find the right page. Yeah, so this, there it is. Okay, yeah. Okay, first let's take a quick note. Measurement in the far field. In the far field. Yeah, so the detection of the electron at a distance let's call it d, much larger than the laser wavelength or the size of the focus or what you may want. Yeah, so a notable exception is a measurement performed on Rydberg atoms using intense radio frequency, an intense radio frequency source. Yes, and a Rydberg atom is an atom where electrons are prepared in a very highly excited state. Rydberg, so these are rubidium atoms, where they were prepared in a state with the principal have a how's this? Wonderful. Okay. So we have Rydberg rubidium atoms, and because the binding energy scales with 1 over n squared, the binding energies here are tiny, so they can be ionized even by a radio frequency source in radio frequency fields with lambda equals to 50 meters. Yeah, and so in this case, because you cannot focus electromagnetic radiations to smaller than a wavelength or so, yeah, the wavelength in this experiment was actually larger than the entire laboratory where the experiment was conducted. And in our cases, this is very different. Yeah, so the wavelengths we use are on the order of a micrometer or so, and this is, well, our lasers, our laboratories are larger than that. So if you're interested, the reference to this paper is Gürtler et al. It's in PRL, Physical Review Letters, in 2004. Okay, so usually this is not the case. So usually the electron has long left the laser focus before it is detected, and also the pulse is long over. And so let's calculate. I don't write down number 3. So let's calculate now the final electron velocity. And in fact, we have done it in the beginning of the chapter. So this would be 2.1.0 actually, and there we find that V naught equals minus sine omega t naught, and this fulfills the initial condition x dot of t naught equals 0. So the electron tunnels at time t0, and it reaches the continuum with 0 velocity. Okay, so we have we perform a time average as before, but previously we actually averaged over the velocity squared. Now we average over the velocity, and this actually eliminates then the oscillatory motion.
Sorry, is it x dot or just x?
This is x dot. This is also x dot. Yeah, because the position we haven't even looked at. Yeah, so here there's some prefactor. Yes, you're right. Yeah, this is because here in the script I wrote it slightly differently. Yeah, so I agree. Let's add the prefactor. The prefactor would be epsilon 0. Sorry, E0 over omega. Yeah, and the mass is 1. And so is the charge. The charge is -1. Okay. Yeah, so this is our initial this is our expression for V0, and now we calculate the drift velocity. So we have here sine omega t minus sine omega t naught dt. And then, yeah, we can of course split the integral, and what we find is that this term here goes to 0. And then if we integrate over this term here, yes, since sine omega t0 is actually a constant, yeah, what we obtain is t times sine omega t naught. And so the drift velocity here is E0 over omega times sine omega t naught. Yeah, this is an equation that we will encounter a few times, and in different ways actually. And now, so this is the velocity. So we can also calculate the energy, the kinetic energy. So that would be 1 over 2m x dot squared. Yeah, so the square is outside of the bracket, and then we can just plug in our result that we just had. 1 over 2 E0 squared over omega squared times, what's that? Oh yeah, danke. Yeah, so 1 over 2 times E naught squared over omega squared times sine squared omega t0. Okay, and now, yeah, so for those who know our numbers, we encountered before the expression quarter E0 squared over omega squared, and that is the Ponderomotive potential. Yeah, so this equals 2 UP. Okay, and so this is, I think, the first example where we find that the Ponderomotive potential is a scaling parameter. Yeah, so, and so this is equivalent to the maximum drift energy. And it's, I think, this time to illustrate this. Oops, that's not what I wanted. No. There we go. Okay. Yeah, so we have here a plot of the electric field. Yeah, that's this one here. And we discussed earlier on that the ionization probability would be a highly nonlinear function of the electric field. Yeah, so this could be, for example, here, this function here. So this is the ionization rate or tunneling rate. tunnel rate. And if I remember correctly, I assumed here that the tunnel rate is proportional to the electric field, to the magnitude of the electric field to the 8th power or so. Yeah, so it's highly confined to the area around the peaks of the field. And then what's plotted here is this expression here. Yeah? So we have 2 maxima per cycle, yeah, because the sine squared has twice the frequency as a usual sine. So we have 2 peaks here, and this is if this is a cosine, yeah, so this is proportional cosine omega t, and this here is proportional sine squared omega t. So what you actually find is here that the maximum of the drift energy is achieved when the electric field goes through a 0 crossing. Yeah? So here's 0. And then at the points where the electric field reaches a maximum, yeah, be it with positive sign or negative sign, then actually the energy of the electron, the drift energy of the electron, yeah, that it achieves after interaction, is close to 0. And then we can also take into account here the tunneling rate. Yeah, so when the electron is close to 0, the tunneling rate is at a maximum. Yeah, so we get from strong field ionization, we get lots of electrons at low energy, and at the highest energies we get no electrons anymore. Yeah, so these 2 UP should never be reached. What's that?
This is the laser's electric.
Yeah, the blue line is the laser electric field. Yes. Yeah, which.
And the electric field is the most, then the electron should concentrate.
Yes. Yeah, this is yes, when the electric field is strongest, regardless of the direction in which it points, yeah, then the tunneling rate achieves the maximum and the electron should come out. And now we plot here the drift energy as a function of this initial time. And so the conclusion from this is that
Sorry, but what does the drift velocity mean? Is it the energy acquired by electrons?
yes, this is the final energy of the electrons. Yeah. So this, if I now scroll back to this plot of the trajectories that we calculate in chapter 1.4, this one here, yes, this one here, then the drift velocity would be precisely this here. Yeah. And in this case, the drift velocity would be 0. Ah, no, sorry, I should draw it here. Yeah, this is the location. And you, the velocity, these graphs here, there are 2 graphs that are almost on top of each other. If I zoom in, you can see it better. But one is offset a little bit towards the positive, in the positive direction. Yeah, the drift velocity would be the average of this dotted line. The average of the continuous line is 0, but the average of the dotted line is slightly different from 0, actually slightly positive. And this, the consequence of the slightly positive value is that this electron trajectory, yeah, the x of t, this drifts away slowly from the center. And now, in our considerations that we just did, we found that there should be more electrons that stay close to the core, that have 0 drift velocity, than those that have non-zero drift velocity. Okay, so yeah, let's take a few quick notes. So first of all, maximum energy equals 2 UP. However, 2 UP is reached at when this here is maximum, so when the sign is at a maximum, which means that when omega t0 for the sine squared to be at a maximum, it needs to be at pi over 2. Yeah, and so so odd multiples of pi over 2. Three pi over 2, and so on. There, the electric field, which is described by a cosine, is 0, yeah, and hence the tunneling rate is 0. Yeah, so no electron yield at 2 UP. And then conversely, when we're at phases corresponding to 0 or pi and so on, at omega t naught equals 0, pi, 2 pi, the electron energy is 0, yes? So E drift equals 2 UP sine squared omega t naught equals 0. But t equals, so it reaches its maximum value. So lots of electrons at low energy, few electrons at high energy. And that's not so unreasonable, right? Many electrons at E equals 0, few electrons at, sorry, not at E0, at E equals 0, at, say E much larger than 0. Okay. So qualitatively, many electrons at low energy, few electrons at high energy. To ease our calculations in the following, we'll take a look at another quantity that you've heard before of, namely the vector potential. So the electric field can be expressed in terms of the vector potential. We can write E of t equals minus dA over dt. And you see already this A is actually the same that I used previously for the laser potential. Yeah. And from this it follows that A of t can be written as the integral from t to infinity over the electric field, and actually with a minus. And well, the electric field of a laser pulse has an interesting property, namely that the integral over the entire field vanishes. The integral minus infinity to plus infinity over the electric field equals to 0. And there are different there are various explanations for this. Yeah, so one is you can think of the of our statement that the free electron cannot absorb a photon. And so if you have an electron at rest and a laser pulse comes by, then at the end of the laser pulse, the electron is in the same condition as before, unless it undergoes scattering, but it cannot absorb the photon. Yeah? And, this is equivalent to it, yeah, because the electric field, the integral, so the electric field is essentially the acceleration, or in other words, the acceleration is directly given by the electric field. So if you integrate over the acceleration, then of course you get the change in velocity. And since this change of velocity must be 0, the integral over the electric field must be 0. Another thing you can think of is that you can express a laser pulse as a superposition of many, many longitudinal modes, yeah? So many sinusoidal functions, and all of them are infinitely long. And then if you take the superposition, you get a short laser pulse. Now, but the integral over each sinusoidal function must also be 0. And so if you take the superposition of them, the integral is still 0. Okay. Yes?
Is this still true for like really short pulses? Because like if I do this to the extreme with the sinusoidal superposition, then I get a delta peak, and
Mm-hmm.
I integrate with a delta peak.
Yeah, that's a good question. If you do it to the very extreme, you could also argue you get 2 delta peaks, yeah, because you can, if you take half of it, and is that true? Yeah, but the integral needs to be conserved. I know what you mean. You can express this as a superposition of infinitely many sinusoidals. Yes, but you could also place the so if you shift everything in phase by pi over 2, yeah, then you don't superimpose them at the maximum, but at the 0 crossing. Yeah, then you get one peak with a negative and one with a positive amplitude.
Even I think even if it's very short pulse, it should be like sinusoidal waveform.
Yeah, but there's, it works nevertheless. I don't know where the limits really are. And one thing that that can occur is in fact scattering, as we discussed. I suggest we take this discussion to the seminar sometime, because the limits of this is actually an interesting discussion, but I think it goes a bit beyond our how much time we have right now. Okay?
Okay, I have another question.
Yes, please.
This victim potential is different from the magnetic one?
The magnetic field is also related to the vector potential.
Yeah, I know, but
Yeah, it's
this
the
electric field, I have never seen a victim potential for.
you can define the vector potential that it describes both the electric and the magnetic field. Yeah, but you take the rod, right? Nabla operator cross B to get the magnetic field. Yeah. Okay. So this integral vanishes, and from this it follows that the vector potential at plus minus infinity equals 0, or some value that we can choose to be 0. Yeah, so we can choose it to be 0. And this is, of course, you just plug in the definition of the vector potential to this integral, and then you get the limits at minus infinity plus infinity, and you find that it's the same value. Okay. And that's the vector potential is actually related to the ponderomotive potential. Yeah, so that's actually 0.6 here. Relation to UP. So the amplitude yeah, so we can find the vector potential by integration. Yeah, so we can, and if we plug in our usual E equals E0 times cosine omega t, then we get E naught over omega times sine omega t. And this is then minus A naught sine omega t. Yeah? So the amplitude of the vector potential is simply E naught over omega. And from this it follows that, we can write it in terms of the ponderomotive potential, or vice versa, write the ponderomotive potential in terms of the vector potential, and we find this expression. Yes, because the ponderomotive potential was exactly 1/4 E over omega. So we can find this. And we can also compare to the drift velocity. Yeah, so this was equation 2.4, if I'm not mistaken. V drift equals, E naught over omega times sine omega t naught. And this is exactly minus A of t naught. Yeah, so in words, the final drift the drift velocity, so the final velocity that the electron achieves, is given by the negative vector potential at the time of tunneling. That's a very useful equation. And with this, we can actually give a recipe to calculate photoelectron spectra. And that is the goal of today's lecture. Yes, specifically. Yeah, so 2.5 recipe to calculate photoelectron spectra. Okay, so to motivate this briefly, let's go back here. So we have our electric field, and from this we can calculate the ionization probability at each point in time, or the ionization rate, I should say. So how many electrons tunnel, and then this curve here. Yeah, so the final the drift energy as a function of initial time. This tells us for each time step what energy is achieved by the electron. Yeah, so we need to calculate two things. We need to calculate the ionization probability or ionization rate at each time step, and we calculate the final energy. And then we have many contributions, and when we sum over them and sort them in a histogram, we essentially obtain a photoelectron spectrum. And that's the recipe here that we briefly describe. So we first define a time grid. Yes, so we have, this is essentially a vector. You can write it as 0, delta t, that's our step size of our time grid, 2 delta t, and so on, tn. At the time grid and a laser field. So this is also now a discretized electric field. Yeah, so this would have some envelope, some envelope function times cosine omega tk, and we can actually allow for a phase offset here. For now we can ignore this, but we will spend some time discussing this phase offset because it's quite interesting. Okay, and now the second step would be to calculate the ionization rate at each time step. Or, since we discretize, we actually, for each little time point in our time grid, we calculate the ionization yield. Yes? Right. Ionization yield per time step delta t. And this is, of course, so this ionization yield, this would be the tunnel rate, dependent on the electric field. And then the yield is essentially the rate times time. And so you get a number of electrons. Yeah, so this, maybe I take a quick, so this is number of electrons tunneling, and this would be so this is a rate electrons per time unit. Okay, and then we calculate the drift energy. Drift energy, V drift equals, well, essentially you sum over the electric field times the time step. Yes, minus because it's a charge, k equals 1 to the end. And as we have just learned, there's a simpler way to do this, namely we can simply use the vector potential. Yeah, so this would be simply AK. Minus AK actually, vector potential. And well, if you want to calculate the drift energy, of course, you calculate V drift squared over 2. And now finally you have to sum up all the contributions. Sum over all, well, time steps. The contributions from, I should say y of tk, and sort them, well, depending on energy. Yeah, so if you define an energy grid, you could write it like the following: energy grid EM, then the yield or the spectrum, the energy dependent spectrum would be the integral k equals 1 to n and then whenever your yk leads to this leads to a certain energy, you sum it up, and then the result is the following spectrum. Yes, so what you get here, this is an example that I calculated. No. Yes, so would be useful to have the laser parameters here as well. But what you see here, so this is a logarithmic scale. Yeah, this is the energy of the photoelectron, the drift energy. And you see there are many electrons here at low energy, few at high energy. And I used here two different rates. Yeah, one is this assumption that it's simply described by a power series, and the other one is a more accurate tunnel rate, which we will derive in the next lecture next week. Yeah, and I think we're at the end. Thanks very much for the attention. And of course, you may ask questions now if you like, or you can also ask them next time.